Hello and welcome to Principles of Mathematics lesson number 18. In this lesson, we're going to learn about multiplication, division, and estimations with rational numbers. We'll look at multiplication and division of rational numbers, properties of multiplication and division of rational numbers, estimation of multiplication and division with rational numbers, and also extension of the laws of exponents to include negative integers, and we'll see how that ties in with rational numbers as well. Here we have some graphics that help us see how we may introduce this to some of the younger students. For example, if we want to multiply 3 by 3/4, we can see multiplication as repeated addition, and basically go ahead and add 3/4 in this manner 3 times. We can see that a total of 9 slices get shaded. So if we actually bring them together into just 2 of the circles to indicate 8 of those, then we just need 1 slice shaded in the next one. So 3 times 3/4 will end up being 9/4, or 2 and 1/4. Again, it's important to see that each of these is representing a whole, right? So these are each broken into 4 parts, so each slice representing a quarter, right? You can also see it as a part of an area, right? Notice that if we start with a 1 by 5, we can always get to a half by breaking that one side into 2 parts. And now when you look at 1/2 times 3/5, for example, you notice that 3 of the 10 boxes get shaded in that, or get covered in that area. That's how we know 1/2 times 3/5 will be 3 out of 10, okay? So when we saw that 1/2 times 3/5 ended up being 3 out of 10, that's what motivates this definition of multiplication of rational numbers, which is probably one of the simplest operations in mathematics. Basically, you want to multiply 2 fractions, you're just going to multiply across. Multiply the numerators to get the numerator of the product, and the denominators to get the denominator of the product. Here we have a quick application. If 5/6 of the population of a certain city are college graduates, and 7/11 of the city's college graduates are female, what fraction of the population of that city is female college graduates? So basically, we're going to find out what 7/11 of that 5/6 is, right? So because we know 5/6 of the population are college graduates, so we want to know what 7/11 of that 5/6 will represent. So what we're doing here is it's a multiplication problem. So like so. So we get 35 over 66. That's the fraction of the population of the city that are female college graduates. We saw last time that 0 was the additive identity for fractions, and the multiplicative identity is once again 1, just as it was in the case of whole numbers and integers and natural numbers. So for every rational number a over b, 1 times a over b is just going to leave it untouched and give you a over b itself, and the same as a over b times 1, which of course makes sense because you're taking 1 of something. How many are you going to get? Well, just that thing, right? All right, the multiplicative inverse, which is also known as the reciprocal of any non-zero rational number a over b, is the number b over a, so that when you multiply a over b by it, you end up with 1. So for a fraction a over b, the multiplicative inverse or the reciprocal is b over a. So for example, if I have 3/4 and I want to get to 1, I need to multiply it by its reciprocal, which is 4/3. Now I notice the 3's cancel, the 4's cancel, I end up with 1. They of course all leave 1's, which we usually don't write, but we can write if we like, okay? So that is very important because it'll help us solve equations later on. Here we state the distributive properties of multiplication over addition or subtraction. And basically you can distribute into a group containing fractions just like we did with integers, right? So just multiply a over b by c over d, add that to a over b times e over f. If it's a subtraction, same thing, except you're just going to get a minus sign in between there. These of course can be stated from the right as well. So if the a over b were written on the right, you would still distribute same as in this case, okay? So those would be the right distributive properties. These are the left distributive properties stated here. So we have the multiplication property of equality for rational numbers as well. Basically, if you know that a over b equals c over d, you can go ahead and multiply both sides by the same rational numbers, and this will be an equivalent equation to that one. What we mean by equivalent equations are equations that have the same solution, basically. Or if there's no variable in them, the same validity. Here we're simply stating that if you have an inequality containing fractions, then you can multiply both sides of that inequality by the same fraction, e over f, and even the direction of the inequality stays the same as long as the fraction you're multiplying on both sides is positive. If the fraction you multiply on both sides is negative, just as was the case with integers, immediately switch the direction of the inequality for a very similar reason to what we saw with integers. You know that things get flipped over, right? When it comes to negative numbers. So for example, we know that 1 is less than 3, right? But as you know, -1 is not less than -3. It's in fact greater than -3. So when you have 1 is less than 3 and you multiply both sides of these by -1, you immediately have to switch the direction, and with fractions it works exactly the same way. Next we see the familiar multiplication property of 0. Take any fraction, multiply it by 0, you're going to get 0. Doesn't matter which side of the fraction you multiply 0 from, the right or the left, you're still going to get 0. All right, here's another application. A bicycle is on sale at 3/4 of its original price, and we know that the sale price is $3.30, so what was the original price? So this is a very typical kind of question for this kind of scenario. So we let x, or p, or whatever you like, be the original price. So we know that 3/4 of that original price is this new sale price. So there's our simple equation that we're going to have to solve to get the answer for what the original price was. So there are different ways of approaching this, but since it's a simple problem with one fraction and no only one term on each side, the easiest possible approach is just to go ahead and multiply both sides by the reciprocal of 3/4, so that you get 1 times x, which becomes x. So 4/3 by both sides. Remember, you never do something to just one side of an equation. So we end up with the 3's cancel out, 4's canceling out, so we just get 1x, which is x, equals 330 times 4/3. Now, we just go ahead and think of this as 330 over 1, so we can go ahead and simplify. Now, I notice that 3 goes into 330 110 times, So 4 times 110 is, of course, 440. So so the original price was $440. When it's a word problem, you always want to present your answer in the proper way by answering the question that was asked. All right, so when it comes to multiplying mixed numbers, there are a couple of ways you can go about doing it. One way is to just turn the mixed numbers into improper fractions and multiply, and then if you want to go back to mixed form, you can. This is, of course, the recommended way. So we know that this mixed number is going to become, remember, 2 times 2 is 4 plus 1 is 5 over 2, and the next one is the same, so we just get 5 halves times 5 halves, which is 25 over 4. Now, should we choose to or need to, we can of course quickly turn that back into a mixed number by dividing long division. So 6 times 4 is 24, leaves us 1. Remember this loop, right? Start at the top and then plus 1 over that. So we get 6 and 1/4. All right, so that's one way to do it. The other way you can do it is clever. We do it mostly for practice. This one, first way, is much more efficient, but we can use the distributive property in this way. We can write each of those as 2 plus a half, right? So now we're going to distribute using 2 plus a half times 2 plus 2 plus a half times a half, or I want to remind you about my favorite way of multiplying when you have more than one term involved. Just do it using a table. Really, really fantastic. So 2 times 2 is 4. 2 times a half, that gives me 1, right? 2 times a half again is 1, and 1/2 times 1/2 is 1/4, right? So watch, we get 4, 5, 6, and a quarter. Same business, okay? So very, very effective way of handling multiplication when you have more than one term times more than one term. If it's just one term times more than one term, you just distribute. But when you have more than one term times more than one term, table is your best friend. Okay, now let's visualize what it means to divide 3 by a half, right? Basically, we want to know how many halves fit inside 3 holes, right? If you notice, you get 2 inside each hole, so for a total of what? 2, 4, 6. So that's a nice way of visualizing why 3 divided by a half gives 6. What if we wanted to know how many eighths fit in 3/4, right? Well, here's our initial 3/4, right? 1/4 right there, 1 right there, and 1 right there. But since we want to know how many eighths fit in there, we go ahead and split the whole into 8 parts. Now we can see 1, 2, 3, 4, 5, 6 can fit inside the shaded area, which is 3/4. So the answer would be what? 6. All right, next we want to look at division of rational numbers. Now, if you have 2 fractions with the same denominator, dividing the fractions is easy. You just basically divide the numerator of the first fraction by the numerator of the second one. But usually the fractions do not have the same denominator, so the general rule for dividing fractions, whether the denominators are the same or not, is as follows. You basically keep the first denominator fraction the same, and you multiply by the reciprocal of the second fraction. So it works out much simpler than we show here in this way. So if you have a over b divided by c over d, basically keep a over b the same, multiply by the reciprocal of the second fraction, and you end up with AD over BC. One way to see why that turns out that way, look at it like this. Imagine we write A over B divided by C over D in this manner as a complex fraction, right? Notice that we can then multiply the numerator and denominator by D over C, and on the bottom, these all cancel out, we just get 1, so this is why we end up with AD over BC. All right, so it's very important to keep the first denominator as is and multiply by the reciprocal of the second denominator. So for example, if you want to divide 2/3 by 9/4, right? The 2/3 stays the same. We change division to multiplication and we reciprocate the 9/4 to get 4/9. If there, at this point, if there are any cross-canceling that's possible, cancelings that are possible, you take care of them. Otherwise, if there's nothing that can be reduced, go ahead and multiply across. So you just get 8 over 27. Or let's say you want to divide 3 by 9/4, right? Well, remember, you can think of the 3 as 3 over 1, right? So keep the 3 over 1, multiply by 4 over 9. Notice here we can reduce the 3 and the 9. You get a 1 on top and 3 on the bottom, so the final result will be 4/3, like that. Okay, here's a quick application. A radio station provides 36 minutes for public service announcements for every 24 hours of broadcasting. What part of the broadcasting day is allotted to the public service announcements? Now, of course, we know here we're going to have to divide, right? So the ratio would be 36 minutes out of 24 hours, but notice that minutes and hours cannot be cross-canceled, and a pure ratio should have no units in it. So what we will do is we will go ahead and convert the 24 hours to minutes. That's easy to do because we know each hour is 60 minutes. So we'll go ahead and multiply 60 by 24. We get 1440. So we get 1,440 minutes. Now do notice that the units cancel out, so we're going to get a pure ratio. Now we can reduce these either by finding the prime factorization of each, or just to do it a little bit more quickly, so to keep our video short, we'll go ahead and try using a calculator. So we'll divide 36 by 1440. Now that gives me a fraction, but if I click this A and B over C button, it'll turn it into it was a decimal, but if I click this button, it'll turn it into a fraction for me. So I get 1 over 40. So 1/40th of the broadcasting day is allotted to public service announcements. So remember, this conversion of units to the same unit is very important in order to get the correct answer. Next, we want to know how many 3/4 minute public service announcements can be allowed in 36 minutes. So here is just another division problem. We're going to take 36 minutes and divide it by 3/4 of a minute. Notice that if you write it as a fraction, you can see that the minutes will cancel out, right? So again, we're going to get a pure ratio. So we get 36 over 1 times 4 over 3. Remember, we multiply by the reciprocal of the second number. Here we notice that we get 12 on top and 1 down here. If we cross cancel the 36 and 3, so we get 48. And that's a pure number, it doesn't have any units, because it's the number of 3/4 of a minute public service announcements that can be fit into a 36-minute slot, right? So 48 of such announcements can fit. Here's another application. We have 35.5 yards of material available to make towels. Each towel requires 3/8 of a yard, and we want to know how many towels can be made. So again, a simple division problem. We're going to divide 35.5 by 3/8. So first we're going to convert this to an improper fraction. So we get 2 times 35 is 70 plus 1 is 71. So we get 71 over 2 divided by 3/8. Now we're going to go ahead and keep the 71 over 2 and multiply by the reciprocal of 3/8, which is 4/3. So when we do that, the 2 and the 4 cross cancel to give us 4 on the top, and we go ahead and use a calculator now. So we have 71 times 4, so 284 over 3. Let's go ahead and convert that to a mixed number. Improper fractions are easier to work with, but mixed numbers give you a much better feel for the quantity that you're dealing with. So we're going to do that, accomplish that by doing a long division. And remember, we're going to do it partially using technology. So we'll take 284 divided by 3. We end up with 94 and change, right? So 94. So now we take the 94 part and multiply it by 3. That gives us 282 with a remainder of 2. So remember, start up here, go there, and then go there. So this plus this over that, right? So we get 94 and 2/3. All right. So now remember, you're not going to want to make 2/3 of a towel, correct? So basically, you're going to answer what? 94 towels can be made. All right, so how much material will be left over? This one be careful with, because a lot of people incorrectly say with 2/3 of a yard. That's not true. Because remember, this is 94 and 2/3 of these 3/8 pieces, right? So to find out how much is left, you're going to actually take 2/3 of 3/8 to get your answer. All right, I hit the wrong button there. So 2/3 of 3/8 is, of course, these cancel out. You get 1 and 4, so we get 1/4 of a yard is how much is left over. Okay, so that's how you do that one. All right, you should be able to do this on your own, so make sure you pause, try it, and then come back. We have a bookstore that has a shelf that is 37.5 inches long. Each book that is to be placed on that shelf is 1.25 inches long. How many books can be placed on the shelf? As you can see, it's just a simple division problem. We're going to divide 37.5 by 1 1/4. And of course, we're going to do that by converting each of these into an improper fraction first. 2 times 37 That's 2 times 30 plus 7, so 60 and 14 gives us 74 over 2, divided by, actually 74 plus 1, sorry. Remember, this number times that number plus that. So 74 plus 1 is 75 over 2. Divided by, this is going to give us 4 times 1 is 4 plus 1 is 5 over 4. So now we're going to keep the 75 over 2, multiply by 4 over 5. Okay? The reciprocal of 5/4. Division turns into multiplication. The second number you use the reciprocal of, okay? So now notice 5 goes into itself once, into 75 15 times, and 2 leaves you 1 and 2. So we end up with what? With 30. So we can fit 30 books. So 30 books can be placed on the shelf. Of course, we can also give the lazy answer without having to repeat what they have asked, and they say how many books can be placed on the shelf. You can just say what? 30. All right, now with estimation and mental math, the techniques we learned for whole numbers we can also use with rational numbers. Let's take a look. Now we want to estimate each of these, and one really good way of doing it is to do the two extremes. Notice that if I round down by just chopping the fractional parts, I get 3 and 7, right? So 3 times 7 is, of course, 21. So now if I go to the other extreme and just round up, so I'll round this up to 4 and I'll round this up to 8, right? So I get 4 times 8, which is 32. So we know that the result will be between 21 and 32, just to give yourself a real quick feel for what that result is going to be. We can do the same over here. So we'll chop the fractional parts. We get 24 divided by 4, that's 6. If we round up, we get 25 divided by 5, which is 5. So we know this one will be between 5 and 6. Now, if you do a quick actual computation, we can see that that's true. Let's look. All right, to do this one, I'll show you how you can do it so you don't have to figure out the improper form. We can just type in, I'll put them in parentheses, so we can put in 24 plus 5 over 7, and then I'll just go divided by, I'll put parentheses again, 4 plus 1 over 8, and then I'll hit enter, and notice a number between 5 and 6. Okay, that's how we would do those estimations quickly. Okay, for the rest of the lesson, we're going to expand our properties and laws of exponents to include negative exponents. So we're going to add a couple of new rules, and we already know a to the 0 is 1 for any non-zero number, where we've looked at whole numbers, but this works for rational numbers as well. Now, this one is new. A to the negative m is equal to 1 over a to the m. You can get a quick feel for why that may be true if you think of it like this. A to the negative m you can think of as a to the 0 minus m, right? Now, if you recall, we had the quotient rule, which told us x to the m over x to the n equals x to the m minus n. Now, if you apply the quotient rule going in this direction, this means that a to the 0 minus m should be a to the 0 over a to the m, correct? Now, notice that a to the 0 is 1. So that's how we get this becomes 1 over a to the m. Okay, so you can use some of the rules you already know to come up with some of the newer rules. You can also do this using patterns. That can be helpful as well. For example, we know that 2 to the 4 is 16. 2 cubed is 8. Notice that that's 1/2 of 16, right? The previous result. 2 squared is 4, which is again 1/2 of 8, which was the previous result. 2 to the 1 is 2, which is again 1/2 of 4, which was the previous result. Now, we're going to keep this pattern going. Notice every time the exponent is going down by 1. So 2 to the 0 should be 1/2 of the previous result, or 1. So keep going. 2 to the negative 1 should be what? Should be 1/2 of the previous result, which is 1. So it should be 1/2 of 1, which is in fact 1 over 2 to the 1. Now 2 to the negative 2 would be 1/2 of the previous result, which was 1/2. So 1 over 2 times 2, or 1 over 2 squared. You get it? So there's another motivation for where this rule may come from. Okay. Now we've already seen the product rule and the quotient rule, the power rule right here. Now this is the power rule for fractions. So basically raise the numerator to the power and then the denominator to the same power. Now this is a useful one. If you have a fraction raised to a negative power, you basically take the reciprocal of the fraction and raise that to a positive power. Now, let's take a look at why that's true. Let's look at a over b to the power of negative m. Now, using this property, we know that that's just a to the negative m over b to the negative m, right? Now, this rule tells me that I can move the a to the negative m downstairs and make it a to the m. Now this one has a sibling rule which says 1 over a to the negative m equals a to the m. So if I use this rule as well, this goes to the top and becomes b to the m, right? So now I get what? I get b over a to the m. There you go. So that's why that one works. And this is just a generalized power rule for a product. So we get a to the m. Just raise each one to that power, a to the m times b to the m. All right, let's put some of these to work with some examples. All right, so here we want to use the laws of exponent to show why this expression is not the same as this expression. So what we're going to do is basically work them out separately and show that they're not the same thing, basically. So let's start with negative x to the power of negative 2. Now, remember the rule that said a to the negative m equals 1 over a to the m, right? The negative exponent rule. So we know that this is going to be 1 over negative x, and the only thing that changes, notice a stays the same, so the base doesn't change. The only thing that changes is the sign of the exponent, right? So that becomes a 2 down below. So now we know that here, when I'm taking negative x and squaring it, that's just saying like negative 1 times x squared, right? So that's negative 1 squared times x squared. Now negative 1 squared is just 1. So we're just going to end up with x squared, right? So we get 1 over x squared. So that's what we get for the left side of this expression here. That's this inequality that's given here. So now let's look at the other side, negative x to the negative 2. Notice this time the negative is not being raised to the power of negative 2. So that's like saying negative 1 times x to the negative 2. So the negative is just going to carry, and this part is just going to become 1 over x squared using this rule. So you can see this one is positive 1 over x squared, this one is negative 1 over x squared. Therefore, we have just verified that negative x to the power of negative 2 does not equal negative x to the negative 2. That's how you approach these problems, okay? With all problems that we do, once we're done, if you hadn't gotten it on your own before by trying, then make sure that you can do it on your own comfortably before you proceed if you want to succeed. All right, here's a couple more. This time, we're going to show that these two expressions are equal. We'll approach it the same way. We'll do them separately and show that they end up being equal to the same thing. Now, let's start with negative x. I hope you've tried it on your own already, not before you're watching this. So that's going to be what? 1 over negative x cubed. Now, remember, when you have negative x and you cube it, that's like saying negative 1 times x cubed. So it's negative 1 cubed times x cubed, right? But remember, negative 1 raised to an odd power is negative 1. So that's like negative 1 times x cubed, which you can just write as negative x cubed, right? So we get 1 over negative x cubed, which we can write more cleanly as by putting the negative on the side and say that's negative 1 over x cubed, okay? This one, on the other side, we have negative x to the negative 3. Here, that negative is just going to carry because it's not being raised to the power of negative 3, but the x to the negative 3 part becomes 1 over x cubed. Notice, they're the same. So we say, therefore, negative x to the power of negative 3 equals negative x to the negative 3. So here I should say, quantity negative x to the power of negative 3 equals negative x to the negative 3. When you want to talk about items enclosed within parentheses, the easiest way to do it is just to use the word quantity. That means whatever follows the word quantity is going to be parenthesized. Then as soon as you say to the power of, as soon as an operation is mentioned, that's when you know to close the parentheses. All right, so how about this one? We want to show that AB to the negative 1 is not the same as quantity AB to the negative 1. So we'll again approach it the same way, do each separately and show that they're different. So let's look at the left side, AB to the negative 1. Well, we know that's going to be A times 1 over B. Using this rule again, x to the negative n equals 1 over x to the n. So now I know that's just like a over 1 times 1 over b, so that's just a over b, right? However, when I look at quantity ab to the power of negative 1, using this rule that if you have x times y to the n, that's going to be x to the n times y to the n, I'm going to get a to the negative 1 times b to the negative 1. And of course, that's going to be 1 over a times 1 over b, or simply 1 over ab. And of course, we can see that they're different. This one came out to be a over b. This one turned out to be 1 over ab. So at this point, we say, therefore, ab to the negative 1 does not equal to quantity ab to the negative 1. Okay, nicely done. Okay, so here we'll take a different approach. Rather than working on both sides, I'll just start with one side and show that we'll end up with the other side. That's another way of showing that the two sides are equal. So we'll start with quantity a to the negative 2, b to the negative 2 to the power of negative 1. We'll apply this rule that if you have xy to the n, that's going to be x to the n, y to the n, okay? And of course, we're going to be using the power rule as well, where you have x to the m to the n equals x to the mn, right? So here we're going to get a to the power of negative 2 times negative 1. What is that? What's negative 2 times negative 1? That's just 2, right? Positive 2. And then b to the power of negative 2 times negative 1, right? So that's also 2. So isn't that what we were trying to show? So at this point we say QED. Remember, quod erat demonstrandum, that which was to be shown. All right, next we want to show that the expression on the left is not the same as the expression on the right. So we'll start with the expression on the left, a to the negative 2 plus b to the negative 2 to the power of negative 1. And we show that it is equal to, well, a to the negative 2 can be written as 1 over a squared, correct? And b to the negative 2 can be written as 1 over b squared, and then the whole thing to the power of negative 1. So now what this means is, remember, x to the negative n equals 1 over x to the n. So we're going to get, let's put it over here. So we're going to get 1 over a squared plus 1 over b squared. So that's basically 1 divided by 1 over a squared plus 1 over b squared, which is 1 divided by, we're going to go ahead and add these two unlike fractions. So that means we need a common denominator of a squared b squared. So to make a squared become a squared times b squared, we need to multiply by b squared, right? So we'll do the same to the one on the top. To make the b squared become a squared plus b squared, we need to multiply by a squared. And of course, we have to do it on the top as well. So we end up with b squared over a squared b squared plus a squared over a squared b squared. So basically we have 1 divided by b squared plus a squared over a squared b squared. Now think of this as 1 over 1, so we're dividing two fractions now, so the first fraction stays the same. We need to multiply by the reciprocal of the second fraction. So we get a squared b squared over b squared plus a squared. To make it a little nicer, I can always write it as a squared plus b squared. And of course, 1 times any expression is itself, so I just end up with a squared b squared over a squared plus b squared. And clearly that is not the same as that. So we say, therefore, a to the negative 2 plus b to the negative 2 raised to the power of negative 1 is not the same as a squared plus b squared. This is a very common error. A lot of students, they see this, they go, oh, I know the rules of exponents. I need to multiply those exponents. Yes, true, you get that. And then I need to do these, and you get that. But unfortunately, this is a very complex situation, as you can see, and it does not simply just boil down to a squared plus b squared. So be very careful not to make that mistake. You can only do that if this were multiplication. In other words, if I have a to the negative 2 times b to the negative 2 to the raised to the power of negative 1, I can say that's equal to a squared b squared. And this is precisely why some students make this mistake. Remember, what can be done with a product is very different from what can be done with a sum. Sums are usually much trickier to deal with, okay? So make sure you understand that before we proceed. All right, here we have another example where we're going to be simplifying these two expressions. Let's do them from scratch. So notice that what I'm going to have to do in order to use my rules of exponents is to try to see if I can write these with the same base, if possible. It's not always possible, but we can try, right? In this case, of course, it is, because I know that 16 is 2 to the 4 and 8 is 2 cubed. So I'm going to replace 16 with 2 to the 4. Don't forget you have to square. And then replace the 8 with 2 cubed. Don't forget you have to raise to the power of -3. Now applying my power rule, which says x to the m to the n equals x to the mn, we get 2 to the power of what? 8 times 2 to the power of, what's 3 times -3? That's -9. So of course we can now use the product rule, which says x to the m times x to the n equals x to the m plus n. Remember the first rule that we learned. So we get 2 to the power of 8 plus -9. Of course, 8 plus -9 is just 8 minus 9, which is -1. So 2 to the -1. Now you normally don't want to give your answers with a negative exponent in them. So we're going to go ahead and use our negative exponent property, which is x to the -n equals 1 over x to the n, to convert that into 1 over 2 to the 1, or just simply 1/2. So that's how you take care of an expression like that. Now here we have 20 squared divided by 2 to the 4. So even though I can't write 20 as a power of 2, I can still utilize its prime factorization. I know 20 divided by 2 gives me 10, by 2 gives me 5, and by 5 gives me 1. So I know I can replace the 20 with 2 squared times 5, right? And then don't forget to square the whole thing. And you're dividing that, or you can just write it as a fraction, by 2 to the 4, right? So notice 2 squared is going to give me 2 to the 4. In other words, we're raising each of these to the power of 2, and then 5 squared is just 5 squared. And down below, we have 2 to the 4, right? Notice how nicely that works out. Now I can cancel out the 2 to the 4s, and I end up with what? 5 squared, which is 25. All right, so, you know, once you get comfortable with these laws of exponents, these really start to make sense. So just make sure you're practicing enough. You should be in great shape. All right, let's look at one more example before we end the lesson. Here we're going to multiply this expression by 10 cubed on the right. So by the distributive property, we need to distribute that to every term. So we end up with 10 cubed times 10 to the -1 plus 5 times 10 to the -2 times 10 cubed. Notice I put the 10 cubed first for this one, and I'm putting it last here. It doesn't matter. Remember, commutative property. All right, and then plus 3 times 10 to the -3 times 10 cubed. Now, we're going to now use the product rule. Remember, x to the m times x to the n equals x to the m plus n. So we get 10. Remember, as long as you have the same base, you can use this. In other words, as long as you're multiplying two powers with the same base, you can use the product rule. Keep the base, add the exponents. 3 plus -1, that's just 3 minus 1, which is 2, plus 5 times, now here I have 10 to the -2 times 10 to the 3, so it's going to be 10 to the power of -2 plus 3, which is 1. So 10 to the 1, which is just 10, plus 3 times, now 10 to the -3 times 10 cubed, that's going to be 10 to the power of -3 plus 3, which is what? 0. Now I know that 10 to the 0 is 1. So now let's see what we have. We have 100, that's 10 squared, plus 5 times 10, which is 50, plus 3 times 1, which is 3. So final answer, 153. Okay? All right. Make sure you try this next one on your own before you watch what I do. Okay. So basically, we're going to use the power rule on each, right? Remember, power rule says multiply the exponents. So we get x to the negative 12 times y to the what? Negative 4 times negative 2, that's positive 8. So the trick is you can either go in 2 steps, write this as 1 over x to the 12 times y to the 8 over 1, and then just get y to the 8 over x to the 12. Or normally, we just go directly to that. We keep the positive powers on the top, we move the negative powers down below. So we could have gone straight from this to the final answer. We can bypass this business once we get comfortable with this stuff, okay? So remember, this only works because that's multiplication, right? If this were, there were a plus here, I wouldn't be able to do this. You get it? But because it's multiplication, we can do this. All right. So make sure that you can handle that, and you should be in great shape. All right, here's a clever problem worth our time. John took all his money from his savings account. He spent $88 on a radio and 1/4 of what was left on presents for his friends. Of the money remaining, John put 4/11 into a checking account, and the last remaining 420 was left to charity. How much money did John originally have in his savings account? All right, one of those problems that can drive you crazy if you panic about it. Just try to think clearly and you'll be fine, right? So some of this information we're actually never going to use, but like the 88 you'll see isn't even going to come in until the very end. So, but in the middle process, let's look. 1/4 of what was left on presents. So why don't we just give this amount that was left a name? Why don't we say, let x be the amount left. After the 88 on the radio, right? All right, so we know that 1/4 of this went to friends, right? Friends' gifts. Of the money remaining, so what do we mean by the money remaining? Well, 1/4 of that was spent, so how much is left? 3/4 of x, right? So now we're working with 3/4 of x, right? John put 4/11 into a checking account, so 4/11 of where we're at went into a checking account. That leaves how much? That means 7/11 of the 3/4 of x. Remember, 4/11 and 7/11, that's 11/11 or 1, right? So this portion basically ended up being this 420 that was left to charity. So finally, we have the equation that we need to solve. So we basically get 21 over 44x equals 420. And Now we're going to solve this equation. So we're going to multiply both sides by the reciprocal of 21 over 44, which is 44 over 21. Notice that's going to cancel out all those. So you're going to be left with x equals 420 times 44 divided by 21. So that's what we're going to compute. So we have 420 times 44 divided by 21. We get 880. Now you got to be very careful not to get excited and assume that that's your answer, because remember what x, okay, so remember what x is. X is the amount left after the $88. So once we have that, now we have to take the 880 and add it to that 88 to get the amount that John started with in the beginning with his savings account. So a clever problem needs you to keep thinking really clearly. And when I said some of the material we don't use, I mean, for example, we don't need to know. For example, we don't need to know the amount that went into the checking account. We don't need to figure it out, but we need to know this quantity so that we can come up with this quantity. But this amount that went into the checking account is not something we need to compute to answer the question, right? So because we just want to know how much he had originally. So take a look at this, make sure it makes sense before you continue. All right, so next we have some equations we want to solve. So let's look at that first one. 2 to the power of n equals 64. If we can get both sides to have the same base, like if you have b to the m equals b to the n, then you can say, oh, m must equal n, right? So that's the principle we're going to use. So we have 2 to the n on this side. I know I can write 64 as a power of 2. The question is what power, right? Notice 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Another 2 gives me 64. So it's 2 to the power of 1, 2, 3, 4, 5, 6. 6, right? So what should n be? Obviously 6, okay? Now, be careful with that one, because we're no longer limiting ourselves to the set of whole numbers or natural numbers. So it's possible for us to have negative answers as well. So if n squared is 49, you need to ask yourself, what numbers can I square to get 49? Now, if you think carefully, you will realize it's not just one number. Here we go. It's actually two numbers. One of them is 7, but notice -7, if you square it, also gives you 49. So here you're going to have two solutions. And the way we usually put that is we put it in this compact form, which basically means n is 7 or -7. Both of them work, okay? All right, so how do we handle that? 2 to the n times 2 to the 8 equals 2 to the 5. Now remember, forgot our equal sign. So the first thing we want to do is get the term which has n in it all by itself. So why don't we divide both sides by 2 to the 8. To get that accomplished. So on the left side now I just have 2 to the n, right? Notice on the right side, I can use the quotient rule. So I get 2 to the power of top exponent minus bottom exponent, right? So now we have 2 to the n equals 2 to the -3. given that we have the same base and these expressions are equal, those exponents must be equal. So at this point we say therefore n equals -3. Pay real close attention to the fact that when we go from this to this, or from this to this, or from 2 to the n equals 2 to the 6 to n equals 6, we're not canceling the 2's. No, there's no such operation. We're reasoning. We're saying, look, we have 2 equal powers which have 2 equal bases. So the only way that can happen is if the exponents are equal too, right? So this is reasoning. It's not cancellation in the traditional sense of the word cancellation. We're not canceling the 2's. We're just what? We're reasoning. All right. So given what I just did, you should be able to do part D, so I'm going to leave that one for you. All right, so most of these you should be able to handle. I just want to give you a hint on a couple, maybe show you a couple. So like on part C, make sure you realize that's -5/2 times. Make sure you convert that to an improper fraction. 2 times 4 is 8 and 1 is 9, so 9/2. Now remember, you're multiplying a negative number by a positive number. The result will be negative. No cross canceling possible, so we can multiply across. So we get 45/4. So -45/4 would be the answer there. Okay, for this part, notice that as long as the only operation on the top and bottom is multiplication, it's perfectly legal to cross cancel factors from the top and the bottom, regardless of which fraction they belong to. You just have to make sure you're cross canceling from numerator to denominator. So here, for example, those two can cross cancel and they will leave you a y on the top, right? So notice the x cubes will cancel out completely. The z squared and z cubed cross cancel and leave you a z on the top, right? So now carefully just see what's left, and you'll see the only thing left is yz. All right, and this one is easier than this one. You should be able to handle it. Okay, so that's how you do those. All right, let's take a look at how we would handle these problems. Like the first one. Notice, first of all, I'm going to write it as an equality of two fractions. So I'm going to put 2y over 11 equals 4/5. Now I want to remind you of the principle of cross multiplication. Remember that if a over b equals c over d, that implies the cross products are equal. So that implies AD equals BC. That is the fastest way to handle a problem like this. So the cross products here would be 2y times 5 and 4 times 11, right? So we get 10y equals 44, right? So now we get y, divide both sides by 10. So we get, therefore, y is equal to 44/10, which we can reduce to 22/5. All right? So the principle of cross multiplication is very powerful. Make sure you're utilizing it. All right, so I'm going to erase this to give us some space to do some other problems. All right, so what about part B? So we have 6/7 divided by y equals 1/6, right? So remember what division of fractions means. You're going to keep the 6/7 multiplied by the reciprocal of y, so it's 1/y, right? So we end up equals 1 over 6. So notice I have 6 over 7y equals 1 over 6. Now we're going to apply the principle of cross multiplication. So 7y times 1 gives me 7y. And 6 times 6 for this cross product is 36. Now all you have to do is divide both sides by 7. And you get y equals 36 over 7, like so. Okay? So be careful with a problem like that. All right, moving on to part C, we have 5/6 minus 2/3 y equals 3/4. We're going to do something clever here. We're going to use the LCD of all these denominators for a different purpose than we normally use the LCD for. We're going to find the LCD and we're going to multiply it by both sides, and that's going to help us clear all those fractions in one shot, which is really nice. Notice that the LCD of 6, 3, and 4 is 12. So here's what we're going to do. We're going to multiply 12 by the left side, and we're going to multiply 12 on the right side. Of course, you know we can do that because we're just multiplying both sides by the same constant, which is perfectly legal, the multiplication property of equality. So now we end up with 12 times 5/6 minus 12 times 2/3 y equals 12 times 3/4. Now, if we've found the correct LCD, all those fractions should get cleared now. Let's see. So 6 and 12 leave me 2 on top, 3 and 12 leave me 4 on top, and 4 and 12 leave me 3 on top. So carefully figure out what's left. Here we have 2 times 5, which is 10, minus 4 times 2 times y, which is 8y, equals 3 times 3, which is 9. See how nice that is? No fractions are left. So now we're just going to move the 9 to the left side, and we'll move the negative 8y to the other side to make it have a positive exponent, positive coefficient. So we're going to add 8y to move the 8y to the right side, and we're going to subtract 9 from both sides to move the 9 over to the left side. So now we get 10 minus 9, which is 1. These cancel out. And on the right side, we have simply 8y, because notice the 9 and the negative 9 cancel out. So now we end up with y, divide both sides by 8, and we get y equals 1/8. And that's how you would handle a problem like that, okay? So this last one you should be able to do after watching this, and that's it for these. All right, so in this problem we have that 1/38 of all rabbits in a country are in one state and 3/5 of them are in another state. What total fractional part of the population is not in either of those two states, right? So basically, if we consider the whole population to be one whole, right? We're just going to do 1 minus the sum of those two, right? 1/38 plus 3/5. Now, you should do these by hand, but I'm going to use a calculator just to save some time on this video. So let me get that for you. Okay, so we have 1 minus quantity 1 divided by 38. Make sure to put the arrow in the right place by hitting the right arrow and put the cursor in the right place, and then plus 3/5, and we hit enter. Of course, that's going to be decimal, so we have to hit this one to get the fraction. So we get equals 71 over 190. So this fraction of the rabbits are in all the other states other than those two. Okay, that's it. All right, here's a good problem. Suppose you divide a natural number n by a positive rational number less than 1. Will the answer always be less than n, sometimes less than n, or never less than n? Why? Now, you have to bring a problem like this to life by just doing an example. So let's just say we take a natural number, say 3. And we're going to divide it by a positive rational number less than 1. So for example, 1/3, right? See, that's a rational number less than 1, right? So we want to know if this is going to be less than the original number n. So here our original number n is 3, or sometimes less than, always less than, or never less than. Well, let's see. That means 3 times 3 over 1, which is 9. So our inclination is to say what? It'll never be less than, right? But let's see if we can generalize now. So we're dividing n by some a over b, right? Keeping in mind that a over b here is less than 1, right? But greater than 0. In other words, our a over b is kind of sandwiched between 0 and 1, right? Notice that this is going to become n times b over a. Now, whenever you have a number between 0 and 1, they behave very interestingly, right? So that when you divide, when you take the reciprocal, right, that's always going to be greater than 1. Think about it, right? And try it for yourself. So, so this is going to be some value greater than 1 multiplied by a natural number. So you're multiplying any natural number by a value greater than 1, you're going to get a what? A larger number. So this result with 9 is not surprising. So the answer would be what? Never. All right, let's look at one more problem before we call it the day. We want to see which one of these is correct. Obviously, this one, the only way to get from here to here is to cancel those b's, which we know we cannot do, right? Because these are terms. So this can't be it. If you look at this one, the only way you're going to get from here to here is if you cancel the a's, which we cannot do. So this is not right. So this better be right? So let's see how. So we have AB plus AC over AC. We know we can factor out an A on the top, the reverse of the distributive property. That leaves us B plus C over AC. Now we see that we can cancel the A's, so we end up with B plus C over C. So this is in fact the correct answer. All right, that should wrap it for today. Take care of yourself until the next video. We'll see you for the next lesson.